Thank you.
Thanks, Miran. I really appreciate the wonderful introduction, and I'm really pleased to be here. I thank all of my attendees for attending my 2022 JCATI Symposium talk. I am a technical integration manager within the NASA Space Technology Mission Directorate, as Miran mentioned. My focal area is on technologies for precision and safe landing of spacecraft onto the surfaces of solid solar system bodies. So my talk today is going to cover NASA development strategy and entry, descent, and landing technologies to both precisely land payloads and avoid landing hazards. Now, the chart package that I'll be discussing is part of one in a very broad portfolio of dozens of technology development strategies that have been put together for more than a year by numerous focal technology areas across the agency. So these packages are going to be released in the coming months in piece parts, and will be available for, they're going to be disseminated and available for the US public and industry to look at what we're targeting in the forthcoming years for technology investments and infusion and commercialization. So what I'll talk to you today is a very dense package of charts that will be available after this meeting for further look into, because I won't go through all the details in them, but then they'll also be forthcoming in broader NASA releases with possible revisions to what's herein. So I'll be going through those today, and I look forward to the feedback later on and the interactions that will occur today, and I welcome interactions in the future with questions, etc. So I'll step forward. So what we're envisioning for the future of precision landing capabilities is to enable missions from small robotic class landers to large flagship class missions, including human landers to the moon and Mars and elsewhere, robotic flagship class missions. We want to enable them to land anytime and anywhere across very benign to very treacherous terrain. And we want to do so independent of lighting so that we can hit anytime and anywhere landing. So these capabilities that I'll talk about today within this strategy are all about reducing the risk to landing of either human or robotic missions, and then reducing the operations time on the surface to accomplish the surface science, the surface exploration, or crew members to get to their pre-positioned cargo, sample return missions, robotic missions to get to pre-positioned surface assets, to help us aggregate our resources for missions that have multi-landings, etc. So these technologies that we're developing are being sought after and to be broadly applicable to all the destinations that NASA is targeting now and in the future. So our focal areas within this envisioned future have been developed over numerous years, leveraging the subject matter experts within our agency, as well as expertise across industry. And there's 6 focal areas within our current investment strategy, and those are pictured herein. We're looking at, for precision landing, developing more highly controllable entry bodies, especially for missions to planets with atmospheres like Mars or Venus or elsewhere. Being able to control the entry more precisely will enable us to shrink landing ellipses, how far we are from touchdown to desired locations. We have several focal system capabilities that help augment that. On the navigation side, we're developing something called terrain relative navigation. It's actually already developed, but we're not stopping with where we are. We're continuing to develop it, and I'll talk more about what it is later. But effectively, it tells you where you are globally to the body you're trying to land on, and helps you make intelligent decisions on how to maneuver to get to where you want to go, again, to shrink landing ellipses. We're developing next generation velocity sensors and range sensors, which are key to both the navigation precision as well as key to doing softer touchdowns of future vehicles. We need to be able to, when we want to land in treacherous terrain, we need to be able to really have a detailed knowledge of the surface that we're landing on to make sure we avoid potential landing hazards, especially for solar system destinations where we don't have high resolution images from orbiting reconnaissance assets. or when we want to land in dark and unlit surfaces, terrain regions. When we do our final descent to touchdown, rocket engines kick up surface ejecta that can impact the spacecraft or cause safety issues, risk the touchdown. So we need to look at plume surface interaction mitigations to facilitate safe landing for both human and robotic missions. And then at the heart of all of these independent technologies is how do we fuse, this is a lot of information, how do we fuse this together? How do we make sure that we can run all the advanced algorithms that are computationally expensive to be able to get this situational awareness on board for either doing purely autonomous robotic maneuvers for safe landing, or to inform our crew members of the situation so that they can be part of the decision making of where that mission lands. And so what ties this all together, what's the conductor behind all this, are all of those algorithms that do information fusion, do decision making, inform the astronauts, but then the computing behind them. And this dedicated computing for precision landing is part of a sister strategy in avionics to enable future multi-core space radiation hardened processing. But then the precision landing computing community is building its computing assets around those processors to be able to do this information fusion. So this is a very broad strategy involving a lot of independent components that come together to enable safe and precise landing. So let me talk a little bit about some of the envisioned future. What are some of the challenges? But before I get there, let me talk about a few of the acronyms that are going to pop up. And this presentation is rich with acronyms because I work for the government and we use acronyms extensively. Some of my charts, when you can acquire them after the presentation, the PowerPoint version has a lot of the acronyms defined in the notes, so just be aware. But some of the key ones are EDL, that's entry, descent, and landing. That applies to bodies with atmospheres like Mars, the Earth, Venus, etc. Whereas when you land on airless bodies or bodies without atmospheres, we call that DDL, or deorbit descent and landing. However, we do often use EDL to represent both. So I'll probably use both of these acronyms through my talk. I'll also use the acronym PLNHA, which is Precision Landing and Hazard Avoidance. That's our catch-all acronym for all that suite of capabilities that I discussed on the prior slide. That we talk about the PLNHA technologies that we need to enable safe and precise landing. So what are some of the challenges? So PLNHA is not yet possible anywhere but Earth. On Earth, we have the Global Positioning System, which provides extremely accurate navigation information. We have pilots that can joystick directly on board a lot of our aerial vehicles. We have short light time delays for ground controllers to be able to joystick autonomous vehicles. We have a level of information that we don't have when we're doing descent and landing on other solar system bodies. We don't have GPS in orbit, for instance, at Mars or elsewhere. We can't joystick things because of long light time delays. Also on Earth, we don't worry about how much fuel mass we have on board because it doesn't cost as much to get those vehicles into Earth's atmosphere to do EDL, for instance. Whereas sending it to Mars to do EDL, you have mass equates to dollars. So this capability is not available anywhere but Earth. We're making inroads, and I'll talk about that later. We can't make one single investment in those 6 focal areas and say we're done. We've closed the gaps for anywhere that we ever envisioned going to. There's no one size fits all for robotic missions, human missions, as well as the various destinations we're targeting. For instance, if we want to go land on Europa, that's an extreme radiation environment. The technologies needed there have to be radiation robust. Or if we land on Venus, it's a very caustic environment, requires a different set of design requirements on how we implement systems that can do this. Human class missions versus robotic class missions also target different precision levels. Right now, the driving human mission requirements are touching down astronauts within 50 to 100 meters, whereas there's some robotic class missions like Mars sample return that's targeting 10 to 20 and potentially up to 50 meters, landing a sample return vehicle to where previously cached samples on the current Mars 2020 mission are left. So there's different precision requirements, which in turn puts different requirements on how you implement your algorithms, the precision and accuracy you need from your sensors, et cetera. And then finally, we've got this anytime, anywhere landing requirement, which ultimately from a sensing perspective means that you need sensors that can function independent of lighting conditions. So you can't use cameras, for instance, to land in dark shadowed craters or on the do descents on the dark side of a planet, because they need illumination, independently illuminated terrain to be able to get the information for algorithms to process. So the rest of this chart gives a written description of those different capability areas. I'm gonna let, if you choose to download these charts later, I'll let you all read that more in detail. I'm gonna go to the next chart though, because I have a graphic that talks about a lot of those. And I've also done it verbally on the introduction. So I want to talk a little bit about what's the status quo? Where are we now? Or where were we, say, a year ago versus with descent and landing versus where do we want to go with PLNHA? So in the status quo, and I've done this generic for different entry bodies. So I'm trying to cover both EDL and DDL. So I genericize initial entry where you would either do a deorbit burn or you'd have an aerodynamic body that needs to be highly controllable to shrink landing ellipses, for instance. So you have an initial entry that occurs. And then you have a powered descent phase where you're doing some guidance maneuvers to either avoid parachutes or back shells that might be jettisoned, say during a Mars landing, or you're trying to do some sort of guidance maneuver to get you to a soft landing. So slow down your velocity, descent velocity to touch down softly, slow down any lateral velocities so that you don't tip the lander over when you touch down, and then you do a terminal vertical descent. So this current status quo results in very large landing ellipses because you're effectively doing blind landing. You're not looking at where am I entering the atmosphere from a global perspective, and then you're just doing maneuvers to softly land. So your information comes from an inertial measurement unit, an altimeter that only senses altitude, and a radar velocimeter potentially that helps you figure out your descent velocities to null lateral velocities and minimize vertical descent. Your only other information for navigation is done during interplanetary cruise, where you use a final descent, a deep space network update to help figure out where you are relative to inertial coordinates. But there's no information on looking down at the planet and figuring out where objects are and using that information to navigate. That's what we do in PLNHA. So in PLNHA, what we do is with that initial entry, where we're looking to say add more highly controllable entry bodies, we add a lot of additional phases subsequently, as well as the sensors that are part of this envisioned future. We do something called intelligent powered descent, where we're leveraging the terrain relative navigation function that uses a reconnaissance map of the surface of the body to compare with onboard real-time acquired images from a camera or some other active sensing that gives you information about what the surface terrain looks like. So you compare those images to your reconnaissance map, and you can use that to effectively triangulate where you are in a global sense. That information is highly valuable because it can help you figure out where you are relative to where you want to go. And then you use your guidance algorithms to then plan effective maneuvers to allow you to divert over to where you want to go. So it helps you significantly minimize your landing ellipses. We follow that phase by something that we call hazard detection, where we use an onboard mapping sensor to take a very high resolution image of the surface, much higher resolution than we can get from reconnaissance maps, so that then we can use the onboard hazard detection algorithms to analyze that map, figure out where hazards are, but then conversely figure out where are my safe landing sites, so that you can make fine-tuned intelligent diverts to avoid those landing hazards and touch down at those safe landing sites. You can use those new maps that you've acquired for something that's subsequently we call hazard relative navigation, where you've now got high resolution onboard images maps to do a TRN-like function to continue improving your navigation precision and ultimately accomplish a very tight landing ellipse versus the status quo where it's still very large. As I mentioned, we're still improving on the available velocimeters and ranging sensors because ultimately those both inform the navigation filters that help with shrinking that ellipse, but then they enable us to more softly touch down vehicles. So let me talk about state of the art because we've started making some inroads into our envisioned future with PLNHA, and we're getting there through development of terrain relative navigation first. On our Mars 2020 mission that successfully landed our Perseverance rover a year ago on February 18th, it touched it down within a 7.7 by 6.6 kilometer landing ellipse on Mars. That's the tightest ellipse we've ever done. The image at left from JPL gives a comparison of the different landing ellipses from our past 25 years now of Mars landings. And you can see from Pathfinder, we've shrunken incredibly down to Perseverance, and Viking was bigger yet. I think Viking itself was on order of 300 kilometers. So we've made huge strides over the past 50 years of Mars landings. And the EDL system of Mars 2020 still leveraged a Viking style entry body. It developed a new parachute range trigger, which analysis showed helped to shrink that landing ellipse some. It used Apollo-based entry guidance, and it augmented that with the new camera-based, so it requires illuminated terrain camera-based TRN system that was developed at JPL called the Lander Vision System. And on top of that, it leveraged the JPL Doppler radar for more precise velocity and ranging. So as I mentioned on the first chart, we're targeting anytime, anywhere landing. So this means even in the dark. So we're making huge strides with the successful landing of Mars 2020 with JPL TRN. Doesn't mean TRN's done. Our envisioned future is to now look at how you do active TRN so that you can have this capability to accomplish those anytime, anywhere landings. So let me talk about our strategy for accomplishing that envisioned future. So what is our overarching goal of this strategy aside from just safely and precisely landing payloads and reducing risk? So we want to, NASA's targeting the development of these capabilities, and I'll talk about how we're approaching that in coming charts. We want to infuse them into NASA missions, but then we don't want to own them. NASA's a prototyping agency. We're not a production house. We want to commercialize these technologies. That's also an extremely important priority to our elected leaders, as well as our senior administration people up at NASA headquarters. NASA is developing a lot of capabilities. We want to spin it off into commercial industries so that it ultimately becomes the next generation of commercial off-the-shelf guidance, navigation, and control capabilities. So we want to buy it back. We want commercial industry to innovate on it and take it further than we do, so that we can be looking at the future lower technology readiness level innovations and capabilities. So how are we approaching accomplishing this goal? So we have numerous ways we're doing that. We have a very robust and strong team of subject matter experts across our various field centers, and they're part of our knowledge base. And we have very high fidelity simulation tools and detailed models that we use, that we pull together studies of various mission architectures and concepts. And we look at the types of landing requirements that we want to accomplish. And we look at the technologies that we're considering and what they would bring to the table to enabling those missions. So we use these SMEs, subject matter experts, and these tool sets to inform us, are we closing the capability needs of mission architectures through the technologies that we currently have? And if we aren't, what technologies should we be considering and then modeling and putting in these simulations to show that we can close these mission gaps? So these are crucial to us to inform what we decide to invest in and develop within the agency and then spin off. But there's a flip side to the value of this knowledge base in these simulations. They also show us the gaps that we're not yet closing. And as we look at new mission architectures and concepts, those as well show us areas where we have gaps, where we need to think of, well, what are technologies that we want to look at next? So this is part of the entire evolution of this strategy that's here. It's not a concrete set in stone forever strategy. It's an evolving one based on what we learn through our internal community, through our work with our external partners, et cetera. We don't have infinite funds, and we also have changing priorities by our changing administration. So what we try to do with deciding what we invest in is to prioritize the technologies that have the broadest cross-cutting capabilities to close gaps that we see in both human and robotic missions. So we try and be smart about our investments in sensors, avionics, algorithms, fundamental research, et cetera, to try and really impact the broad nature of NASA missions. We see huge value in doing, especially in entry, descent, and landing, in leveraging multiple test paradigms. We learn a lot in our simulation environments, in our first principles analyses, but the rubber really meets the road when we take out technologies into the field, get real data with them, and take that back to our labs, analyze it, and figure out what went right, what went wrong, what do we need to revise. And then it's just part of this circle of lab work, field testing, improvements to really help accelerate and mature the TRL of capabilities faster. And I'll talk more about some of these test paradigms because we have some really neat ones within the EDL community. And then finally, we constantly engage with the NASA technology transfer process. We engage with public-private partnerships through various solicitation mechanisms that I'll touch on throughout. And we try and foster both commercial spin-offs, but also keep an eye on what innovations are coming out of private industry and academia so that we can figure out spin-ins to our strategies and to the work we're doing within NASA. That's all a part of how we mature technologies and then help make them part of that future COTS, commercial off-the-shelf capability. All right, so this chart here is a bit of visualization of what I just spoke to. Excuse me for a second. So I felt it was important to put together a little bit of visualization about how we do this process that I just verbally described on the government side, and how we also leverage solicitations and look to commercial innovations to help drive our process of developing this strategy, reassessing it, spinning things off, spinning things in, and then folding that back to evolve the strategy. So I've mentioned our knowledge base. Our knowledge base is critical throughout every step of our technology development process. We're always looking at that concept studies using the numerous simulation frameworks that we have across the agencies to do analysis and high simulation testing. And we use our focal projects to help drive those concept studies, look at those different models and simulations and architectures to really inform us about the investments we're making. We develop projects both in the low TRL technology readiness level aspects of technologies, as well as mid TRL. So this is low TRL is TRL 1 to 3, mid TRL is 3 to 6. We have several focal projects or academic partnerships, small business solicitations, larger public-private partnerships that are a part of how we develop low and mid TRL technologies, how we incubate them into things that we commercialize, and how we're also assessing things that we can spin in. And then, as I mentioned, we're always engaging our tech transfer throughout this process to see where things are within NASA for spinning out or for soliciting to help incubate things from the commercial sector, or to see if there's something we're missing or that would be better that we can spin in and leverage from commercial. So on the commercial side, we have lots of focal mechanisms. I have a chart on SBIRs later, that's small business innovative research, and there's an arm of that brings in academia and research institution partnerships that I'll touch on later. So we try and incubate our solicitations for that based on what we're learning in our projects and in our knowledge base, because we want to see the innovations that the research institutes and small businesses can bring into the picture. We, through STMD, have several solicitation mechanisms for public-private partnerships that we call tipping points or announcements of collaborative opportunities. These have been highly successful in the commercialization of some of the initial PLNHA capabilities, and I'll touch on those later. And then we have mission-specific solicitations through, for instance, the Human Lander System is soliciting commercial capabilities for the future planned missions, human missions to the moon. So those solicitations help us not only spin off what we're working on, but also inform us about what partners are doing and help us spin things into the things we're thinking about and we want to invest in, or that we want to continue soliciting in the future. And I have to just say, the government doesn't drive all of these innovations. There's a lot of things that we learn from that are going on out in industry that come out of, sort of nowhere sometimes and really give us fresh thinking about new sensors or algorithmic approaches, et cetera, that could come in and feed into this problem. Ultimately, what we're trying to drive at with all these things is developing capabilities that infuse into our missions and future US commercial missions. So I want to talk about our approach. That's all high level discussion about the things that we're doing, but let me talk about our actual approach. What are we doing within our projects? Then I'll talk about some of the specific projects to accomplish all of these capabilities. So on the highly controllable entry body side, the work that's going on in there is coupled not just within my PLNHA strategy package, but we have a sister one that's developed by Michelle Monk, our EDL principal technologist across the agency. She's developing it for large 20, we call it the 20-ton package. These are very large payloads that would be required for taking humans to Mars, for instance, or even larger robotic missions. So those very large payload missions benefit greatly from having highly controllable entry bodies. So the work that's done within my strategy areas is simulation environments and looking at how can we leverage these new novel entry body architectures and add intelligent control to them, add new types of guidance, add new types of sensing to improve the guidance, navigation, and control. The aerodynamics side and how those bodies are shaped and how we get the better performance from an aero perspective, that's done on the 20-ton lander side. And that strategy package will come out in the coming months through NASA headquarters. There's going to be larger releases. So there'll be more detail on that one when that package comes out. On the hardware side of precision landing and hazard avoidance, I mentioned that NASA doesn't have infinite funds, and we have to be very thoughtful about the things we go and invest in. Internal to the agency, so there's numerous methods of sensing that we can use to go and accomplish the types of envisioned future that we have. We could use LiDAR sensors, you can use new novel radar. There's discussions of thermal sensors, advanced sonar for some things. We can't invest in everything. So what we've chosen within the agency over the last several years is to invest heavily in developing longer range, higher precision LiDAR active sensors, because with LiDAR, we can accomplish the anytime, anywhere landings. So we're developing capabilities in those areas to enable active terrain relative navigation ultimately, but also to enable hazard detection so that we can do descents on the dark side of the moon, for instance, and land in dark, unlit craters, et cetera. These establish baseline capabilities for the agency that then we can commercialize and then build upon through other solicitations and pull in things like novel new radar methodologies, et cetera. We're also investing in the computing architectures. We have a sister strategy in avionics that's actually developing our radiation hardened multi-core computing and doing it from a commercialization perspective. So we work closely with that strategy and that community on how PLNHA leverages that multi-core computing. And as I mentioned, we're developing PLNHA specific computing architectures that take those chips, put them into our computing assets and leverage them. And because at the end of the day, the higher computing performance allows us to have fewer avionics boxes to support the numerous sensors and the high computational cost algorithms that are a part of PLNHA. The algorithms are really the next touching point. We have significant investments across the board in guidance, navigation, hazard detection, plume surface interaction, trying to to figure out the types of algorithms that can be brought to bear on our problems, machine learning-based algorithms, et cetera. We have a very extensive effort in plume surface interaction modeling and validation right now to help us inform how we might mitigate it in the future. We have efforts, and I'll talk about some of these projects in a moment, on developing mapping tools and processes to give us navigation quality, train relative navigation maps that can be used for both PLNHA as well as surface operations. And then I mentioned hazard detection and avoidance algorithms. Wanted to touch briefly on the various test modalities that we have in entry, descent, and landing, because they're very rich. We have assets that we leverage within the agency, as well as assets from the commercial sector that have become very valuable to us in helping to accelerate the TRL and then infuse our capabilities. So we, within the agency, have numerous labs for very high resolution detailed computer simulations of dynamics and sensor models and algorithms that help us really mature from an algorithmic perspective what we need to then put on flight processors. We have facilities that do focal component testing. This picture is probably hard to see, but we have a facility where we've got a train relative navigation camera that stares at a super high resolution monitor that provides terrain imaging, rendered terrain imaging of places, so we can test how the flight cameras and the flight software process images to then figure out global positions for terrain relative navigation. We have facilities that have dynamic gantries that can give 6 degrees of freedom positioning, where we can do lower cost descent and landing type operations with sensors to stimulate the sensors, get real sensor information of synthetic terrains from multiple sensors, so we get dynamic timing consistent measurements that are then put into the real flight computers, processed through the real algorithms, and then fed into a simulation that then in turn drives the dynamics of the gantry system, so we can get at a lower cost some closed loop testing with real sensors, real algorithms, real avionics, before we start stepping into higher costs of field testing on aerial vehicles. We make extensive use of aircraft, helicopters, drones for doing various aspects of testing of component sensors and their algorithms. And then we can step into something called suborbital rocket demonstrations, which have been in existence for roughly 15 years now. All of these platforms now come from commercial industry, and they've been incredibly valuable to the EDL community in particular, because before these vehicles existed, the first fully integrated closed loop means active use of the sensors and the algorithms to affect the spacecraft position. The first true closed loop test of an EDL system was on the actual mission EDL. So that can be $1 billion mission risk. So it's very expensive, the types of validations that would occur on a component-wise level that we can now do more cheaply with suborbital rockets, where we can integrate the real sensors, the real avionics with the algorithms, do flight testing in very relevant dynamic environments. Some of them go up to space, so we get some vacuum environments, and then evaluate the performance of something before we then put it on spaceflight missions or potentially lunar demos. And with the arising of something called commercial lunar payload services, we have the potential to do higher risk lunar demonstrations of technologies before we put them on to billion-dollar flagship class missions. Before I move on, I wanted to touch on all the various incubation mechanisms that we have to look at low TRL capabilities, new innovations, help spin those into NASA and help spin things out into industry. We have robust academic partnerships, and I have some slides on that later, that we enter into for the development of a lot of our PLNHA algorithms. I have a strong partnership with Meron, who introduced me for developing novel new guidance algorithms, and Washington's Professor Bechet Atikmasha for algorithm development. We have partnerships with numerous universities, I think a dozen or so across the US in my area alone. We leverage SBIR and STTR solicitations. As I mentioned, that helps us both spin out technologies to help create supply chains for components that we need to help in the commercialization, but it also helps us spin in what small businesses are doing and actually help in our commercialization of some of our full technologies that I'll talk on a little bit later. We've been highly successful with STMD's tipping point solicitations. In 2018, we issued a tipping point solicitation for the commercialization of terrain relative navigation. We had 2 winners, awardees from that solicitation. One's in Washington, is Blue Origin. Those tipping points were incredibly successful to help take NASA-developed TRN technology and get it into the hands of Blue Origin and Astrobotic to help spin it into commercial industry. In 2020, we issued a tipping point for the development of a next-generation suborbital rocket vehicle to do higher and faster closed-loop guidance, navigation, and control testing, which will help accelerate the maturation of those closed-loop integrated PLNHA systems, both from NASA as well as from commercial industry. PLNHA is becoming very highly sought after by the 12 to 14 CLIPS companies that are working on these lunar landing, private lunar landing vehicles, as well as the HLS companies that'll be taking developing the vehicles that take our astronauts back to the moon. These have been incredibly successful. We have a current solicitation that's open. We envision continuing to use this mechanism to help throughout the commercialization process of what we're developing. We have a new, through our Flight Opportunities Program, which has contracts with suborbital vehicle providers, we have a new precision landing, nighttime precision landing challenge to help with the incubation of active sensing systems to image and map terrain that can be used for hazard detection and ultimately for terrain relative navigation. We're very excited about that one. That's an open solicitation competition right now. And then we use NASA industry workshops to help talk about the things that we're investing in, learn what industry needs, just have a broaden the community, the knowledge base that we leverage in the development, execution, and evolution of our strategies. For instance, we had a 2021 lunar mapping workshop between our focal project Luna Maps that I'll talk about on the coming chart and broader industry and academia that was hugely valuable about what kind of mapping tools and processes do we need to develop high resolution, high quality navigation maps for landing on the moon. So these are very valuable mechanisms for us. All right, I see you need to pick up the pace. Let me touch on several of our focal projects. So our projects are ultimately within NASA. Our focal projects are what really implement and make the advancements in the technologies that we turn around and commercialize. Our SPLICE project, Safe Precision Landing, Integrated Capabilities Evolution, and I have another chart on this following, is leading the development of a lot of our LiDAR technology that we're developing for next generation velocimeters as well as hazard detection sensors. They're also leading the development of the dedicated precision landing community, computer architecture, and they're in the process of commercializing some of the technologies that have been developed through the investments. Our Luna Maps project that I mentioned briefly on the last chart, it's developing the tools and processes leveraging what the agency's worked on for Mars missions and for other landing missions for lunar mapping with LRO and Mars mapping with MRO, Mars Reconnaissance Orbiter and Lunar Reconnaissance Orbiter. It's leveraging and pulling together the tools and processes from Goddard Space Flight Center and the Jet Propulsion Laboratory to figure out, a framework that we can use internally as well as disseminate and make available to industry and academia to generate high quality navigation maps for use on the moon and Mars, extrapolate that information for how we would do high quality maps for Mars, Europa, elsewhere. We have a plume surface interaction project that is doing the modeling and validation planning for how we understand and measure and look at plume ejecta, so that in turn in the future we can take that information and turn it into mitigation tools and algorithms and sensors that would be on board vehicles. On the Science Mission Directorate side, we have investments in the Europa lander concept. It's developing PLNHA capabilities for the very unique environment of Europa, where you have high radiation and the surface is covered in ice penitentes, basically spears. So there's unique requirements for the landing there. However, those technologies that are being developed there have broader mission applications. So we're watching how those evolve to make sure that we keep an eye on them for potential investment and cross-cutting infusion into other mission applications. Let me touch on SPLICE because it's a good example of all of the comments that I've made about how we're commercializing things. So SPLICE is working on several of those focal 6 investment areas. It's doing some continued work in TRN. It's been shepherding the development of NASA advanced velocimeters. It's working on NASA advanced hazard detection, and then it's doing the computing. What I really want to call attention to is the green and orange highlighting. The green is what SPLICE is now buying from commercial industry. So it's COTS. We're not building this stuff in-house anymore. We're acquiring it. We're buying IMUs. We're buying cameras. We're licensing and buying terrain relative navigation algorithms. We're now buying the technology transfer of our Doppler LiDAR technology that's being implemented via phase 3 small business innovative research project. And then some of the architectures we're using for the compute element, they're industry standard architectures. We're leveraging COTS parts. And then all these other pieces in the computing, all the algorithms and our hazard detection LiDAR, we're in numerous early conversations on how to license that technology and get this stuff ultimately spun off into industry from a hardware perspective or licensable to industry through NASA software release. So all this stuff comes back into a very aggregated plan that has a timeline associated with it. So we have all these areas that we're investing in, but how do we accomplish them in a meaningful manner and under constrained budgets? So at this chart here, which I'm not going to go through in super detail, at left, I have those 6 technology areas that are part of our envisioned future. And at the top, I only have the timeline through fiscal 22. We decided to extract the timelines beyond fiscal 22 because we always have fluctuating budgets and then we have changing priorities from our elected leadership. So we wanted to just showcase that we have envisioned futures that we're going to be persistent with to develop and then infuse and commercialize these technologies, but the timelines can change because of budget pressures and directives of our leadership. These 6 areas are being implemented by those focal projects that I touched upon and several others, as well as being influenced. In green, I have some of our commercialization initiatives. They're being influenced and evolved by our tipping point awards, by our small business innovative research projects that help us then infuse these technologies. We're driving towards commercial demos of commercial TRN in the coming years, so through commercial lunar payload services and eventually through HLS. We're driving towards commercial demonstrations of Doppler LiDAR technology. We're targeting lunar demos of the SPLICE payloads and commercialization of the SPLICE payloads, all of which, from my very first chart, go back to target infusion into broad classes of missions to the Moon, Mars, Europa, etc. And this strategy will constantly evolve based on the progress, the successes, the failures, the setbacks, the innovations from industry that come daily and through every annual cycle. Let me just briefly touch on some summary points. So our current investments, as I've mentioned, are what's driving our approach to closing the gaps, closing those envisioned futures. But we have a lot of next steps that we have to maintain so that this stuff is seen to fruition. We will continue our concept studies through our knowledge base, through our subject matter experts, our investments in low TRL and SBIR solicitations, our academic awards, our public-private partnerships, because that's what commercializes things. We're going to be continuing to target technology tests on field tests to mature plume surface interaction mitigation capabilities to fold that back into our missions. We want to do lunar demonstrations of our technologies. We want to see through the development of radiation-hardened spaceflight computing, because that's our next generation of how we shrink avionics and do more. We're going to see our Europa LiDAR investments through for those unique environments. But there's still things that we need to focus on. Active TRN is becoming likely very valuable for human lunar missions where you might have to do descents on the dark side of the moon. We need to be looking at investing in those more fully. And as all these technologies evolve, we need to think about what's next. You know, we're developing 3 independent sensors right now, but we always want to push for making things more compact, lower the mass, because that comes back to dollars for space. We want to develop multi-mode, multi-capability systems and sensors. So let me just go to summary and recap very briefly. So our strategy that's herein is develop safe and precise landing capabilities for anytime, anywhere global access. It's about reducing risk. So we want to infuse this into our missions, but then ultimately commercialize it. That's our goal. And we're approaching this by developing cross-cutting systems, sensors, and avionics, sustaining a robust community within NASA and now broader through commercial industry. And it's broadened by things like this symposium and through our publications, through AAA and other events that bring our communities together. We're implementing this across NASA centers so that we have we're leveraging the best and brightest of what's in our subject matter expertise across the agency. We're leveraging our partnerships. Whoops, my slide just jumped. And then we're leveraging our technology transfer process to help transition this into COTS. So before I say thank you, I've added 2 charts that come from our early stage innovation program that actually focus on how students, faculty, and universities can get engaged. There's websites for these. I'm going to touch on these briefly so that I have a few minutes here. Our Space Technology Research Grants program has 5 focal areas where students and faculty can get engaged, propose cutting-edge innovative research, but also look at the specific things we're soliciting where we see gaps and needs for future research. We've got over 800 awards and it engages more than 100 universities. So please visit this website to find out more information. We've also got our SBIR and STTR program where small businesses and research institutions can get engaged in annual solicited phase 1 activities where we put in those the areas that we see as really desiring next generation developments. In my area, we've been seeking multi-mode detectors and next generation entry sensors, and we change these solicitations annually, and those can lead to prolonged development through phase 2s and phase 3s and other solicitation opportunities. So please visit that at sbr.nasa.gov. And with that, I'm going to conclude my talk and hand it back over to Mehran.